Alright, good day class. We're going to go through our lab number 3. We will look at Ohm's Law. We will discuss resistivity, that resistance is a property of all materials. And we're going to review why some materials are conductors, why they are insulators, and some are semiconductors based on that property of resistivity. We are also going to discuss simulation. This is the technique where we use the computer to solve for voltages and currents in a circuit. I'm going to introduce you to the tool, which is Multisim Live. So let's go ahead and get into it. On lab 3, let's go through the objectives quickly. Again, we will cover the following topics. Introduction to Ohm's Law, and we already talked about Ohm's Law in our previous lab. We said Ohm's Law is a relationship that just describes the equation that describes the relationship between voltage, current, and resistance. We want to talk about circuit analysis and circuit simulation. The rudiments, again, we want to review the steps to connecting a circuit. And of course, we have a lab worksheet for this lab. So we don't have a lab report like the first lab, but we have a lab worksheet that you will complete. What are the objectives? We want to follow the experiment instructions to conduct standard experiments. So we're going to follow the instructions. We're going to utilize Multisim for simulation of electrical circuits. Again, this is a tool that you can use going forward in the lab. We want to also communicate lab results in a report. Of course, this time we're going to do a worksheet and not a report. At the end of this lab, you should be able to explain Ohm's Law to anyone. You should be able to discuss discussion and analysis of the lab and simulation results. So you need to discuss the results that we obtain as well. Let's proceed. So this link is not live for the tutorial, but we will update it very soon. Next page here is our content. It talks about analysis and analysis of circuit using Ohm's Law and problem-solving method. The problem-solving method is important to demonstrate synthesis of the problem. That is, to demonstrate understanding of the problem. We need to use the problem-solving method. It also demonstrates that you are able to select the correct equations to solve a given problem. So what is that problem-solving steps that we'll talk about? First, when you're given a problem, you need to write these 4 steps. Number 1 is given. What are you given this problem? State what you're given, state their values, and also include the units. Then list what you need to find, right? State the value that you are told to find, include the units if appropriate. Step 3, equation. Include the equation or conversion factors that have relationship between the given and the unknown. So you're asked to find X. What is the relationship between what you are given and what you're asked to find? Most times that is a formula. Write all the formulas that pertain, right? Then number 4 is your solution, where you're going to write your solution to the unknown using the equations that you already identified. So you can see that solving the problem is about identifying the correct equation that will relate your input to your output. Steps to a successful circuit simulation. Number 1, select the correct symbols. So you need to know the symbols for the items you need to simulate. For example, we're going to use batteries, resistors. You need to know the symbols for them. Number 2, connect the circuit as shown in your described in your handout. Step 3, update the component values to reflect the values given. So when you select your components like your resistors or your battery, you need to update the values with the values that you are given. Step 4, place the symbols for measurement as shown. So you need to put the voltmeter, the ammeter, so that you can obtain the right measurements. Step 5, run the simulation. Step 6, copy the simulation results to your document. Step 4, record the data from the simulation results in the given table. Okay. Here we have an example of analysis. Now I already opened this. I'm going to share it with you. Example of analysis. Okay, where is it? Okay, give me a second. Okay, here it is. So here is the example of Ohm's Law analysis. Let's make it a little bit bigger. So we are given a circuit here. What is our circuit? This circuit is a basic circuit. It has 1 battery. It has a fuse here. So this symbol represents a fuse. And it has 1 resistor. So this is just a one load is in this circuit. And here we see, of course, a symbol here representing current, and it has IT by it representing the total current. So we are given this circuit, and then we are said solve this using analysis, right? So you're told, given the circuit, find IT, which is the total current, PT, which is the total power, PR, which is the power rating, and FR. Okay, I don't know what FR means, but we'll find out. Okay, so again, I'm using the problem solving method. You can see here we have given Vs is equal to 16 volts and R is equal to 1 k ohm, right? That's what we're given. Fine. What are we told to find? We're told to find IT, PT, PR, and FR, right? Okay, FR stands for fuse rating, and the fuse rating is normally the total current in the circuit times that safety factor of 1.2, right? So the current times 1.2 is going to be our fuse rating. So here we have the known. What do we know? Okay, we then write the equations that we know that relate our inputs to our what we are told to find. So here, this is Ohm's law right here. Ohm's law is the relationship between current, voltage, and resistance. So here we are saying that IT is going to be V divided by R, right? I is V divided by R. And you see we are given Vs and we have our R. So of course that is the equation we're going to use to find our current. Again, we have an equation for power, that power is equal to V squared over R, like we discussed in class yesterday. We also have the equation for power rating, that power rating is equal to power times 1.2, which is essentially saying power times 120%. Then we have the equation for fuse rating, that the fuse rating needs to be the fuse, the total current in the circuit, times 1.2, right? And so again, here in our solution, of course, you can see we have the same equations, but we now substitute our values with the units, and we have our answer with the units. So again, 16 divided by 1000 gives us 0.016 amperes. And to write this in milliamps, it's going to be 16 milliamps. Likewise for power, V squared over R is 16 volts times 16 volts divided by 1000 ohms. It gives us 0.256 watts or 256 milliwatts. Power rating, again, is 1.2 times our total power, which is going to be 3.07.2 milliwatts. Fuse rating, current times 1.2, so we have 19.2 milliamps for our fuse rating. Of course, if you go to buy a fuse, you may not get a fuse that is rated this low. Now, when you select a fuse, you think about, okay, what is the application? What is the total current my circuit is going to use? And of course, you also think about, okay, what is the current that's going to damage my components? And most times you take the next fuse up. The same way we take the next resistor up for the resistor power rating, we take the next fuse up. Okay, so notice here we did not calculate the power rating for the resistor, because we only have one resistor. The power rating for the circuit is going to be the power rating of the resistor. So let's summarize Ohm's law. Ohm's law tells us the relationship between voltage, current, and resistance. It says that voltage is equal to current times resistance. So if you just memorize this, you just change the subject of the formula, and you're able to get the other, you're able to calculate resistance and also current if you're given the two of these. Very simple equation. Again, for power, we said that power is equal to voltage times current. And if we substitute Ohm's law in Ohm's law, we can get the other equations for power. So if we substitute I here, if we substitute this equation, V is equal to I times R for V, then we end up with I times R times I, which is I squared R. So this is the equation for power. And if we substitute, again, V over R for I, we are going to get V times V over R, which is V squared over R. Again, the resistor rating is 1.2 times the dissipated power, and the fuse rating is 1.2 times the circuit current. Okay, we're moving very quickly. Of course, you have your quiz right here and your reflection activity on Ohm's law. The next thing we have that you need to do is your lab assignment. So let's go ahead and look at what this assignment is about. So this is what the assignment looks like. For this assignment, you need to use Multisim live online. So if you remember in the course materials I gave you on this page, I told you that there are two simulation softwares that you can use for circuit simulation. That is where we get the computer to solve the circuit, the circuit analysis for us. You can use LT Spice, which is a free software that you can download. or you can use the Multisim Live Circuit Simulator online. And this is another tool that you can use. So just click on the links and sign in. For LTSpice, you need to download the software. Now, there are lots of free tutorials out on the internet showing you how to use LTSpice to simulate and how you can get your current and how you can get your resistance from that circuit. So again, these are the tools that you're going to use to complete your circuit. For today, I'm going to use Multisim Live Online Simulator to complete the circuit. Let's go through the lab handout, and then we'll get to the part where we have the procedure, where we are going to actually follow these instructions to obtain our results. So the objectives of the lab is to develop an understanding for the concept of resistance and to utilize analysis and simulation to solve unknowns for a basic circuit. Now, when we talk about analysis, we are talking about how we can use equations that describe the relationships between components to get certain unknowns. So again, anytime we talk about using equations to solve the problem, this is called analysis. Simulation, on the other hand, is where we use a computer to solve the problem. Now, in our case, we are using a graphical interface to create the circuit and to put the values, and we are using the computer to measure those values. So the computer will calculate the answer, and this is what we are getting. So the equipment, like I said, you need the NI Multisim software. So let's look at our theory. Like I said, we'll talk about resistance and resistivity, and we will see that all materials have that property of resistivity, and this is how we can actually design resistors. So let's look at the theory. When current flows through a material, electrons collide with the atoms in the material and restrict the movement of electrons through the material. A different material offers different levels of restriction. This property of resisting the flow of current is resistance. And like we discussed earlier, the property of resisting the flow of electrons through a material, for whatever reason, that is resistance. So some materials are conductors, and they will have lots of free electrons, and the electrons can move very freely through the material. With other materials, it's a bit different. This property of resisting the flow of current is resistance, and it is measured in ohms. A material's resistance is directly proportional to its length. So that means the longer the material, the more resistance it's going to have. It is also inversely proportional to its cross-sectional area. That is, the larger the cross-sectional area, the lower the resistance. The resistance of a particular material can be calculated using this I just highlighted is a coefficient of resistivity times the length divided by the area, where rho here is the resistivity of the material in ohm meters, and it is specific to the material type. L is the length in meters, A is the cross-section in meters squared. A material of very low resistivity is a conductor, while a material of very high resistivity is called an insulator. Materials have a high resistivity between materials that have high resistivity on the range between a conductor and an insulator are called semiconductors. Most materials, temperature affects this resistivity. So this coefficient of resistivity is affected by temperature for some materials. For some materials, as the temperature increases, this coefficient of resistivity increases, and that is called positive temperature coefficient. While some materials, when the temperature increases, the resistance in the material decreases, and this is called negative temperature coefficient. Again, we already said that materials that are designed, or components that are designed to have fixed resistance, are called resistors. The resistance of manufactured resistors, that's a typo here, is not perfect but within a particular tolerance. Like we said, no manufacturing process is 100% accurate or precise. That is why we have tolerance, so that we can have quality control. So too, when we manufacture a resistor, the resistance is accurate to a certain degree, and of course we use the tolerance, sometimes 1%, 5%. So our measured resistance would be anywhere plus or minus 5% or 10% or 1% from the designed resistance. Okay, resistor sizes and materials determine how much heat the resistor can dissipate. In class, we said that the cross-sectional area of the resistor determines affects the power dissipation, right? So resistors are designed when they are manufactured. They have a resistance, yes. They have a tolerance that tells us how precise the resistance is going to be when we measure it, and they also have a power dissipation or power rating that gives us an indication of how much power it can dissipate without being damaged. Hence, all manufactured resistors have a power rating indicating the maximum power dissipation that the component should dissipate before being destroyed. Resistors can also be fixed or variable. So we said a resistor is manufactured to have a fixed resistance, but we also have variable resistors that are designed so that the resistance can change by the user. A variable resistor is designed so its resistance can be easily changed. Variable resistors are called potentiometers or rheostats based on a number of pins. And so we have a number of symbols here. So if you look at the first symbol here, we have a symbol for ground. Then we have a symbol for a variable resistor. So you can see the symbol of a resistor here with an arrow through it. We have this one is a potentiometer. So now this one has 3 pins. So again, if you measure between these 2 pins, you have a fixed resistance. And if you measure between these 2, it's going to give you whatever resistance is between the arrow here. So as you move the arrow, the resistance can go from 0 all the way to the maximum, right? So this is like a selector pin. Then we have a regular resistor, and of course this is a battery, symbol for a battery, right? Next we have resistor, power ratings, and potentiometer examples. So this is from Circuits 101 or Electronics Hub. If you have a look here, we can see that we have different resistors here with different power rating, right? And notice that the size is different. So the larger the component, most times, the more heat it can dissipate, right? And of course, there are different types of resistors. So based on the construction method, a resistor may be able to generate different amounts of heat as well. But in this case here, these are all carbon resistors. And generally, the higher power rating, the resistor is going to be bigger. On the left-hand side, we have a number of potentiometers here. Of course, you can see we have a rotary potentiometer and a singleton. So this is all different ways that they can come in. We have a linear potentiometer. The basic concept is that when you turn the selector, essentially what you are doing is that you are changing the location of the selector pin, and that in turn changes the resistance that is coming out on these 2 pins, what it is between one selector pin and another pin of your potentiometer. You also have digital potentiometers where it's like an IC, and you can actually program it, and it's going to change some switches inside of the IC, and on two of your pins you can have the change in resistance as well. Okay, resistor color codes. We already discussed that for especially the carbon resistors, like those that are in your kit, and those that if any of you doing electronics, you will use resistors all throughout your program. The color codes help us to identify the value of the resistance very easily. So instead of going to measure it, because sometimes the resistor is in a circuit and you cannot remove it to measure it, the color code helps us to identify it so that if we need to replace it, we can go ahead and do that as well. So again, the first 2 bands represent numbers, the third one the multiplier, the fourth one the tolerance. And sometimes we can have resistor color codes with 5 bands, where the first 3 are going to be digits and the next one is going to be the multiplier or the number of zeros. And I think we have a quiz on that coming up. Again, the tolerance tells us the error in manufacturing. So when you measure that resistance, it could be plus or minus whatever the tolerance is. All right, so again, we have a picture here showing what I just discussed. This one is a 4 band. So the first 2 bands are the digits. So again, if we have an example here, say if we had for this resistor, this is yellow, so this is 4. The first digit is 4. The second digit is 7, is purple. The multiplier is brown. So we just add 1 0. So we have 4, 7, and 1 0 here. And the tolerance is gold, so it's going to be 5%. So this is 470 ohm plus or minus 5%. Okay, what is Ohm's law? We already said Ohm's law describes a relationship between current, voltage, and resistance. And again, it is represented mathematically as V is equal to I times R. And if we change the subject of the formula, we can get I and R as well. All right. Again, based on this equation, a circuit is said to have 1 ohm of resistance when we have 1 volt. 1 volt causes 1 ampere of current to flow. So this is, you will need this when you describe Ohm's law. When we have a fixed resistance, okay, because of that equation, if the resistor is fixed, anytime we have a change in the voltage, it's going to cause a change in the current. And anytime we have a change in the current, it's going to cause a change in the voltage, because it's going to be, we will see that voltage and current are directly proportional. So if the voltage increases, the current is going to increase as well. So example experiment that is normally done, we have a fixed resistor and we simply increase the voltage and we notice the change in current, and then we plot that on a graph, right? And if it is I over V, and then so after we plot it on a graph, we normally take the slope of it, and we will see that the slope is going to be the resistance. Okay, let's come down. So here's a problem. It says, given the following circuit, calculate the total current, the total power, the fuse rating, and the power rating. Show your results using analysis and simulation. So you're going to follow the same steps that I did in this example right here. You're going to follow the same steps to complete this problem right there. So what is the procedure? Use analysis to calculate the total current, total power, fuse rating, and the power rating. Add your results to your lab worksheet. Again, I already gave you a sample worksheet that you can follow. So you're going to use the sample worksheet to solve this problem. Any questions about this? This is number 1 in the procedure we're given. And the problem is very simple. 50 volts here, 1.2K here, right? The second step says, simulate the circuit in NI Multisim, run your simulation, include a picture of your simulated circuit, and your results on your lab worksheet. Then step 3 says, complete the other sections of your lab worksheet and submit it as an assignment. All right, very simple. So at this time, this is what the lab worksheet looks like. It says here, draw a picture of your circuit, include the analysis steps. So you put your analysis here, include the picture of your simulation results, picture goes there. Include your results, so you're going to copy your results into this here, into this table. Then you're going to answer the questions. How does your simulation results and your analysis results compare? What do you think? Simulation in the future. And of course, in the appendix here, I included a picture of the experiment that is normally done, where you have a fixed resistor and you change the voltage and you measure the change in current, and you can get the slope of this here. And using the slope, you can calculate the resistance. So I didn't ask you to do it for this. I just gave you the example. So I also gave you the example here in the appendix for if I took the slope of this graph up here, how can I calculate the current from it? And if you were to do it in Excel, this is what you would do. So this might be something you will get in a future experiment. So at this time, let me go ahead and share my screen. So we will do the simulation for this. We'll not do this for this one. We'll do it for a simple example, right? So if you go to your when you go to multisim.org and you log in here, right? You're going to create a circuit. So when you log into Multisim Live, this is what you see. You sign in. Can you see my page? Let's make sure everyone can see me before I go further.
Yes, sir.
All right, great. So you log into Multisim Live, and this is what you see here. Of course, we're going to go on create circuit. And then we need to select the right part. So of course, if you open your lab in front of you, you can see the circuit. Let's go down. See our circuit. All right, so again, we have 3 components. We have a ground, we have a power supply, we have a resistor. Right, so we need to add these 3 components and connect them together. And of course, we need to then measure whatever we need to measure. So we go right here and we select the ground. Let's put it right there. So click on it, and then you select the ground and you place it on your circuit.
Then we go and get the resistor. Let's select the right component and we place it on our circuit. If we want to rotate it, I'll go ahead and rotate mine so it looks like the circuit. And then we need a battery, right? So if you go down here on sources, we can now select a DC voltage and put it above the ground. All right, so it's done. Now I can connect it. That's the second step, right? The first step is going to be to make sure I put the correct values for everything. Okay, let me just make it a little bigger in case you have any problems seeing it. All right. So here we'll connect this guy here. All right, so it's now connected. So step 2 is done. Now I need to change the values. So what value should I use? 1.2K and 50 volts. So let's just double click on this and see if we can type it in. Okay, on the right hand side, we can type it in 1.2K. See if that works. Okay, it doesn't work. So I'm going to type in 1.2K is the same thing as 1200. All right. So this is fine. Let me see if it will take K. Does it take K? Okay, so it takes K. Let me change it now to 1.2K. All right. Then this one should be 50 volts. So I'm going to change it to 50. 50. Enter. All right, so now I'm ready. So I've completed step 3. I selected the components, connected them, changed the values, and now I'm ready to simulate. Right. So what can I get from the simulation? Of course, I can get the total voltage and the power. Maybe I can get. So let's go on to see that. Let's go on interactive. Okay, no, we go on this V probe here, and then we can select what we want. In this case here, let me select voltage and current, so they will be together at the same place. All right. So now it shows me the voltage and the current. And what else do I want? Now I'll just also place a probe at the bottom here for voltage, so you can see that after the resistor the voltage is 0, right? So in other words, all our voltage is dropped across this resistor right here, right? So after we place the probes here, the next step is going to be to run the simulation. So we press play, and you can see it tells us what the voltage is, it tells us what our current is, and based on that we can calculate our power, right? So you are going to then take a screenshot of this. How do you do that? You just press your Windows button, or however you do your screenshots. I like to use the snipping tool, and you just cut, just do a new snip so you can get all your information. And this is what you're going to put in your datasheet. So let's copy this here. All right, let's see. Okay, so I have this here. You can see here I can easily calculate my power by multiplying voltage by current. So it's going to be 50 times, and I can calculate my power. So whatever you cannot get from measurements, you can simply calculate them for your simulated values. Okay, this is the end of the lab. So like I said, when it comes to hair, you're going to draw a picture. You need to include the picture of this. So the only thing I may need to do, I may need to share a Microsoft Word copy of the lab worksheet so that you can more easily put your stuff in there. All right, well, again, I hope that this was helpful and that you'll be able to just follow the simple steps to do the simulation. Nothing difficult. And again, this is just introducing you to the tools so that when we get into the series circuits and the parallel circuits and whatnot, then you will be able to do it with the analysis, following the steps, and you'll be able to do it with the simulation as well and compare those results. And since we have the physical circuit board, right, you will be able to so you'll be able to do the analysis. That's why we do it with the equations. You'll be able to do it with the simulation, right, getting the computer to calculate it, and we'll be able to do it with actually on the circuit board, so we can actually measure and compare these 3 results for the rest of the circuits going forward. So in other words, the next lab is going to have analysis, simulation, and measurements as well.